Welcome to session 2 of Unit 2, and in this session we'll be looking at thermodynamics. By the end of the session, you should be able to explain the forms of energy in thermodynamics, and you should also be able to show how to formulate the first law of thermodynamics, and as well as explain with illustrations the term PV work. Energy in thermodynamics manifests itself in three forms, and in our previous session we spoke about energy. Now, these three forms of energy include heat, work, and that of internal energy. Heat, in in other words, is energy in motion due to temperature gradient or difference. That is to say that the temperature gradient or difference is a necessity for us to be able to classify it as what? Heat. And various textbooks use different symbols for heat. Some will use capital Q, others will also use small q. Work, which we define as energy resulting from translation of force through a distance. And usually work can be experienced either as mechanical energy or electrical energy. To be able to drive the formula for work, most often we are referring to mechanical energy, which we describe as work is equal to force times distance, force times distance, or work is equal to force times the internal energy possessed by a system. What is internal energy? The internal energy refers to the energy possessed by a system by virtue of its state at a particular time. That is to say that, or in other words, it is the energy possessed by each particle in an isolated system. The total internal energy of a system is the sum of all kinetic energy and potential energy for each particle in a system. And usually the symbol for internal energy is represented as U, is represented as mu. And this leads us to the first law of thermodynamics. What is the first law of thermodynamics? It states that the total internal energy of an isolated system is constant or zero. Now, in all cases, in all these cases, you realize that the internal energy of water is the same. That means that the internal energy of the system is a state function. The value of a state function does not depend on a particular part, that is, previous history of the system, but it depends only on its present condition. So, when we say state function, it is a function or property whose value depends only on the present state or conditions of the system, but not on the path taken to arrive at that condition. Examples of state functions are, you can talk about pressure, you can talk about volume, you can talk about temperature. However, work and heat are not state functions. Work and heat are not state functions. For example, if we define our system as 50 of water at 25 degrees Celsius, our system would have arrived at that stage by the cooling of 50 of water from 100 degrees, or by melting 50 of ice from 0 degrees to water at 25 degrees. That is to say, the internal energy or the energy change is equal to the energy or the final energy minus what the initial energy possessed by the system. And we can therefore say that the energy change depends only on the initial and final states of the system, but not how the changes actually occurred. Now, let's look at how we formulate the first law of thermodynamics. Suppose any closed system undergoes a process by which it passes from one state to another. Let's say stage A to stage B. If the only interaction with its surroundings is in the form of transfer of heat, which we are representing as Q, to the system, or the performance of work, W, on the system, then the change in internal energy will be the internal energy of B minus that of what? A. Then we can say that, or this actually equates to the heat energy or heat plus the work done. So for us to be able to write a mathematical expression of the first law of thermodynamics, then we can say that the internal energy or the energy change is equal to the change in heat plus change in what? Work. And the most common type of work encountered in a chemical system is the expansion work, also called the PV work. That is what you call the pressure volume work, and this is as a result of volume change in the system. So if you have a particular a system which can be or which is compressible, then we can actually have an initial volume and a final volume. Now let's take this example for instance. You realize that the initial we have C3H3 plus 5 moles of oxygen going to give us 3 moles of carbon dioxide plus 4 moles of water. Now assume that the reaction takes place inside a container which is fitted with a movable piston. So this is the container and this is the movable piston here. Now if we push this piston up, what happened? The volume increases. So you realize that here we have a volume increment. This is where our initial volume was, and this is where our final volume is. Now what is pressure? Pressure is equal to force over area. So you realize that there's a change in the volume, and this takes us back to calculus when we are trying to find our differentiation or our differentials. So for us to be able to find that, then we need to integrate our function or our work done. So if we integrate our work done, then we are going to have from our initial volume to that of our final volume. So we are integrating our work done from the volume increase from initial point 0 to our final volume. So and this gives us W is equal to Fx. But we know that pressure is equal to force over area. Therefore, we can make force our subject, which will give us pressure times area. Now, we can now substitute this PA into our initial formula Fx, which will give us pressure times area times the change in volume. So this AX represents our change in volume, and then the X actually represents the distance, but then AX represents our change in volume. Then our A represents the area, P is the pressure. So for us to be able to simplify this formula, we write it as W is equal to PV, or W is equal to PdV, where dV represents the change in volume. The expansion in volume that occurs during a reaction forces the piston, that is in our previous example, outwards against atmospheric pressure. The amount of work done is equal to the pressure exerted in moving the piston in the opposite direction of the atmospheric pressure times the volume change. That is to say that our work done now becomes what? W is equal to negative P times change in volume. Now why the negative sign? The negative P implies or means that the work is being done by the system. The work is being done by the system. So there are two terms you need to take notice: work done by the system, work done on the system, work done by the environment, or work done against the environment. So the work is being done by the system. That is why the P is having a negative sign. And because the expansion or the expanding gas does work on its surrounding in pushing back the atmospheric pressure, the work will definitely have what? A negative sign. Now let's take this example and see what is happening. We have 3 moles of hydrogen reacting with 1 mole of nitrogen to give us 2 moles of ammonia. Note, the moles in this case is directly proportional to the volume. Therefore, they can be used interchangeably. So when a reaction takes place with the concentration in volume rather than expansion, the work has a positive sign. If there is no expansion, work done is 0 because the change in volume will be 0.